All right, well, here we are. We are on our part 3 of the sums, right, addition of fractions with what we like to call an unlike denominator, meaning our denominators are not the same. We're going to go through another series of these just to continue to get this practice in, not only to understand the how, but also the why this works and why it doesn't, and so on and so forth. So here's where we were at, right? We have learned so far that if I have fractions and their denominators are the same, well, then that means I'm working with the same size pieces. And if I'm working with the same size pieces, right, we showed through a model, but really through the algorithm, that just means my denominator stays the same. Nothing changes there. The size of my pieces isn't going to change when I add things together. What does change is the amount I have. And if I first had 1 out of 8 pieces, and then I had 3 out of 8 pieces, well, now I just add that numerator, I have 4 out of 8 pieces. This has been what we talked about in previous videos. So when my denominators are the same, and all I gotta do is keep my denominator the same, like slide it on over, and just add my numerators, and I have an answer. Well, what we've been exploring now in these past couple of videos is this isn't always the case. This is not always the case whatsoever. And that at times we will often end up working with fractions that are not the same, do not have the same denominators. They are unlike. And so we have a process now, and we're going to use this video to just like really run through that process mathematically of like, how can we walk through and figure this out? And it all starts with this idea, right? First, are my denominators the same? Yes, then do all the work. But no, I got to start thinking about equivalent fractions. And sometimes that means I can change one fraction to have a denominator the same as the other, because that's what I want. I want 2 fractions that have denominators that are exactly the same so that I can compare and add these 2 together. Or like, do I need to change both of them, right? So this is where we're at. We've been thinking about this idea of like, okay, well, if I model these, I could try to model them. It might not always work out in ways that I can partition one over the other to make equivalent fractions. So we've been focusing on using the LCM, and we've talked about that. This is another unit. This was done. There's videos on this. And what we said is, oh, well, if I find the least common multiples between my denominators, then I'm going to know what the best way to partition my models into to see what I have. So that means we have 4, 8, 12, 16, 20. I'll just stop there for now. 3, 6, 9, 12, 15. Oh, there it is, there it is, there it is. So we can see that in this case, the LCM of these is 12, which means if I take my model and cut them both into 12s, it's going to work. So now let's take this to the model to help us do this, right? Now let's take us to this piece. So one thing we're starting to connect with is that when we make these models, it's a lot like an array, right? This is going to be force. So what I'm going to do is I'm going to, let's see, we'll put it into 4 pieces. Okay, and then I have 3/4 of it. So I'm going to shade in 1, 2, 3. Okay, and then this is going to be thirds. So maybe we'll go this way, and I have 1 of them. Okay. All right, well, now we want this to be cut into 12ths. We want 12ths. So let's think about that. If I looked at this as an array, I'm gonna get rid of these arrows so I have some more space. If I think about how to draw that model and I think about this as an array, well, I have 2 on this side and I have 2 on this side. 2 times 2 is 4. I don't want 4, I want 12. That's what we just realized. We want these fractions to have a denominator of 12. So then I could go, oh, okay, well, how about this then? If I keep my 2 on this side, what if I partition this side into 6 pieces? Because 2 times 6 is 12, right? So now we can change and partition. So let's see, I want 6. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. There's 6. And I guess you could argue I could kind of move one over a little bit, but this works. This this is 12 pieces now. So this 3/4, I'm going to change this denominator. It's now a 12. And instead of 3 sections shaded, I have 1, 2, 3, 4, 5, 6, 7, 8, 9. So I've just converted 3/4 into 9/12. That's what I did here, okay? So now let's think about the other one. We have 1/3. So how are we going to make this 12? Well, again, let's think about an array, right? This is what I love about when everything starts connecting, all these skills we've done. Well, I have 3 on this side. Well, then maybe I just could partition this side into 4s, because 3 times 4 is 12. So let's do that. Let's go boom, boom, boom. And I now have 12 pieces. Well, that worked out really well. So that I no longer have 3 pieces, I have 12. And instead of having one of them shaded, I have 1, 2, 3, 4 of them shaded. So now that I put those two together, they're both 12s, right? Thanks to the LCM, I thought about how to do that. So now, well, let's just use that algorithm, what we know. When the denominators are the same, keep it the same, slide it on over, and just add what you have. And what I have is 9 plus 4, which would be 13. So this is going to be 13 12s, which does, as I can see, my numerator is larger. This is going to be more than one. And we could, let's think about how much, let's put that, let's see what we can do here. So, well, we have 9 over here, 10, 11, 12, 13 total. So there's already 9, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I'm just moving those over, right? So there's 1 whole. So let's see, we have 13 12s equals 1 whole, and then 1/12 was left over. So that's how we could write that in the other form, right? And there will be videos on that talking about mixed numbers and improper fractions or top-heavy fractions. So let's continue to explore this again on all the little steps we're doing here. Let's do this with all the steps we're doing here. So what do we want? Let's do 1/2, and let's add 4/5. Okay, so here we are. We got to think about how it is. Maybe not even maybe. I think it'll probably be good for us to model it before we even start thinking. Let's just draw the model we have, because sometimes I forget to do that, and that can make a mistake. So there's 1/2, and then we got to put this in fifths. Let's see, so that'd be 4 lines. 2, 3, 4, and then I have 4 of them shaded. So 1, 2, 3, 4. Okay, cool. So those are our models. But now, if we think about it, we got to partition these so that they have the same denominator. We got to partition them into the same size pieces. And to help me do that is that great work that we've already learned with the LCM, because that's going to tell me, well, what's that common number I can cut these into? So I'm going to do that. And again, I'm going to use the LCM of my denominators. The least common multiple of 5 and 2. I'm using my denominators. I want to clarify that. So 2, 4, 6, 8, 10, 12, 14, 5, 10, 15. Okay, cool. I just saw it. So it's 10. So this is what they share. If I cut both these models into tenths, then I'll be able to add them together because all my pieces will be the same. So now let's use that concept of an array to help me partition, because I already know I need 10 pieces, and this is 5, right? So 5, whoa, that's always makes me laugh when that happens. 5 times 2 would equal 10. So that means I just got to make 2 pieces here. So I'm going to do it like that. And that should be 10. Let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Cool. So now instead of 4/5, right? Instead of this 4/5, that's what this is here. Instead of this one, I now have 10, and I got 1, 2, 3, 4, 5, 6, 7, 8 shaded. So I have 8 tenths. That's what I just did. This was the conversion. I just took 4/5, I converted it, I made an equivalent fraction, and now it says 8 tenths. Right, and let's do the same thing over here. So again, we want tenths. So I'm already write that. I know I want to do it. And let's use our knowledge of arrays, right? Like this is 2, right? So 2 times what would equal 10? Well, 2 times 5. So I got to cut this into fifths. So 1, 2, 3, 4. So now there's tenths. There it is, right? Sorry, that's crowded. I'm going to try to do an example with a little more space so it's not as crowded. And so here we are. Instead of 1/2, we now have 1, 2, 3, 4, 5 tenths. And that's the same thing. So I took 1/2 and I turned it into 5 tenths. I took 4/5, I changed it into 8 tenths. Those are equivalent. So now that my denominators are the same, we can just follow the rule. Here's the rule. Denominator stays the same. Add your numerators, right? Add those up. So 5 plus 8, that's 13. And there's my answer. It's 13 tenths. 13 tenths. And again, we can convert this into a mixed number, which would be 1 3 tenths. Like both of these are acceptable answers. I'm going to keep putting that out there. But for now, if you can get to 13 tenths, you're good. Okay? All right, so let's tackle one more. Let's just tackle one more. I'm going to try to space it out better. And I'm gonna go through this one. So we have 1/3. Let's take 1/3 and let's add 4 ninths. Okay, now this might be a little more complicated. So let's just dive in. Let's get going. So I'm gonna draw my model first. And this is 1/3. This is 4 ninths. Nines. Let's see. That means 8 lines. 1, 2, 3, 4, 5, 6, 7. That doesn't quite turn into 8, so I do this a little cheap. There we go. All right, and I have 4 of them. So 1, 2, 3, 4. Okay, so that's the modeling. But now, again, my denominators are not the same. So I'm going to use my knowledge of the LCM of my denominators. Why did I write 4? 3, 3, and 9. And I'm going to see what they have in common. So like 3, oops, man. Ooh, I'm like trying to rush, so I'm making mistakes. 3, 6, 9, 12. And this is 9, 18. Oh, so it's 3. I mean, it's 9. Ugh. It's 9. That's what they share. Okay, so this is going to work out pretty good because then I don't have to change 4 ninths. It's already ninths. That's what I wanted. So this can stay as 4 ninths. This one, on the other hand, 1/3, I got to change so that the denominator says ninths. And again, to help me draw the model, I'm using the concept of an array. I got 3 on this side. So I want 3 on this side because 3 times 3 is 9. So I'm going to partition it like this, and that gets me ninths. 1, 2, 3, 4, 5, 6, 7, 8, 9. Man, that's a lot cleaner than the other one. That's pretty fun. And now let's look at how many are shaded. Instead of 1/3, I have 3 ninths. And they are equivalent. They mean the same things, right? So now that these are ninths, let's just put it together. 3 ninths plus 4 ninths equals 12 ninths, right? Denominator stays the same. And what that really is that would be, I need 9 pieces to make a whole. So that would be 1 whole. And then there'd be 3 left over because I have 12 of them. So 3 out of 9. So there's your mixed number. Here's your top heavy or improper fraction. And there is how we can use addition for fractions that have unlike denominators. I want to encourage you, keep asking questions, watching videos, and putting things out there. We may update with another video depending on how things go. Like if this works, great. If you need to see some other steps, we'll definitely post another. As always, thank you so much for your hard work, and we'll see you really soon.